Okay, the next presentation will be presented online by Manuel Bauer from University of Hohenheim. The presentation will discuss nutrient element recovery potential of 3 different feedstocks after the TORWASH process. A little bit about Manuel. He obtained his bachelor's and master's degree in bio-based products and bioenergy from the University of Hohenheim, where he's currently studying for his PhD and working as a research associate and lecturer in the Department of Conversion Technologies of Bio-Based Resources. So, Manuel, are you there?
Yes, I'm there. Can you hear me?
Okay, well, the floor is yours.
So, thank you for a nice introduction. Hello, everyone. I hope you're having a nice time. I joined this research project very recently, like 3 months ago. I'm substituting Gero Becker here. You probably know him. He's in Spain right now in another meeting, so he can't be there. And so I wrote my email address here in case you have several questions which I'm not able to answer. I will forward this to Gero because he's the expert on the topic, but I'll do my best to provide you the necessary answers. So you saw this quite a lot now. What our part was try to recover or think about strategies how we can recover the nutrients from the TORWASH process, either from the solids or from the liquid effluent. And one of our main products, or our main targeted product, was struvite. It contains nitrogen, it contains magnesium and phosphorus. So this is a multi-component fertilizer which we think has a lot of potential. Usually struvite is a white crystalline powder, so as you can see we do have some impurities here, but I'll talk about this a little bit later. Just very brief, some of the analysis, because I heard that you also asked about it. What we do have in the dewatered solid, so in the filter press cake, is a certain amount of nitrogen, of course of carbon, and of phosphorus, which was our main focus here and which is interesting for us. Here you can see that in the paper sludge solid, you do have like 100 times the amount of phosphorus compared to the other 2 biomasses, which was quite interesting. If you look at other minerals, it's not, I heard this before, it's not mainly heavy metals, they're also in, but we also have a lot of manganese, for example, or calcium and magnesium and so on. So those are minerals which we can find in those biomasses. And we also had a look at the heavy metals. As you can see here, there is some amount of heavy metals, mostly in the paper sludge residue, and not so much in the other 2. And if you also combine this with the carbon content, which is quite high in the waste olive pomace in the orange peels, we thought that one first possibility maybe would be to even use those 2 residues directly on soil, or at least this would be a possibility or something one has to try. If you now come to the liquid effluent, it looks a little bit different. We do have some phosphorus in here, but the scale is different. So we have milligrams per liter here, we have milligrams per gram in the other. So it's much less calculated on the volume or on the mass. We do have some nitrogen, and there are huge differences between the biomasses. So we have about 1,000 milligrams per liter in paper sludge, where you only have roughly 300 in orange peels and even less in the waste olive pomace. And between 8 and 20% of this nitrogen is in the form of ammonium nitrogen, so plant or bacteria available inorganic nitrogen. Potassium was also interesting to see because we do have a lot in waste olive pomace, roughly 1/3 in orange peels of that, and even much less in the paper sludge. So it would also be interesting for the future to recover this somehow. And if we now have a look at the most of the hydrocarbons or of the analysis we usually do with hydrothermal process water, just the main constituents of that, like furfurols and sucrose and so on, which together show or give the COD, the chemical oxygen demand. We see that we do have not so much organic in the paper sludge, we saw it before. We do have a lot in orange peels and a little less in waste olive pomace. So as you heard before, this makes it interesting for anaerobic digestion. We also had a look at some of the phenols and some of the polycyclic aromatic hydrocarbons. just to have an idea if this maybe is toxic or is somehow making problems if you want to use it for plants or for the anaerobic digestion. And what you can see here, for the polycyclic aromatic hydrocarbons, we did not see any problems, at least for those three biomasses. And for the phenols, it really depends on feedstock, what you can find there. Now, the post-digested liquid effluent, I didn't get it from the last presentation, but as far as I know, there were some dilution factors used so that the batch test worked. And so we calculated back from these dilution factors, which were given on the original amount. So that's why you see these numbers in this table. This is just a calculation. So we can estimate how much of the nutrients do we have inside there. And I did not go into detail for this presentation because this dilution and also the addition of several nutrients to start the process distorts the result. And so we did some trials with this, but I did not include it here because I think it's not really very repeatable or tells us a lot about the process and how we could do it in reality. What is interesting, I mean, we had it before, is of course that by anaerobic digestion, you get a greater amount of plant available or bacterial available nutrients. So as you can see here, the amount of ammonia or ammonium nitrogen from the total nitrogen is increased by a lot via the anaerobic digestion. Good. Now let's come to our mass flows. Here you see the paper sludge and here olive pomace and orange peels. These mass flows were done by from the data of the pilot process and from our analysis. And what you can see is not so much for the sludge, but for the olive pomace and the orange peels, you have some strong underestimation. So if you add, for example, the phosphorus on the left and on the right, it doesn't add up to 100%. This often happens in pilot processes. And so we just have to take this with a grain of salt that we know it is the right direction, but it's not 100% what we get out in these processes. Now, what's interesting is that if you look at the phosphorus and especially at the solid, for us, we found almost exclusively in the dewatered solid from sludge a lot of phosphorus, not in the dewatered solid from olive pomace and not for orange peels. So for our general strategy of how we try to get the nutrients back, how we recover nutrients, is some form of acid leaching from the solid. Only makes really sense in this case because in the other two there simply is no phosphorus. What you can also see here is that nitrogen partitions differently. So we have the majority of nitrogen in the liquid effluent in this case. Here we have the majority of nitrogen in the solid, so it really depends on the feedstock. And what's also interesting is that most of the potassium, because it's potassium salts are water soluble, so most goes to the filter press effluents. So phosphorus of the solid is interesting for the sludge, not so much for the other two. And in general, we can say that any strategy which wants to focus on nutrient recovery has to focus on the liquid stream in some way. Good. Now, more or less what you've seen several times now. This is just the process scheme we have from paper making, wastewater treatment, to the sludge, the TORWASH process, and then we have the dewatered solid and the filter press effluent. And generally speaking, the first possibility to recycle those effluents would, of course, to directly feed them back to the wastewater treatment, because here we also see it needs some nutrients for the bacterial growth. This, of course, has to be checked and has to be tested because, as you saw, we have the presence of several phenolic compounds, and they could maybe have a negative influence. Second possibility is the anaerobic treatment, as we heard before, and use the nutrients in the post-digested effluent for the wastewater treatment. Again, this would be interesting because a lot of nutrients are mineralized during the anaerobic digestion and a lot of the possibly harmful organics is decomposed. So maybe this would be an interesting path. And the third, our main interesting part, was this one. So we tried to recover nutrients from the effluent and the dewatered solid in the form of struvite. And of course, struvite, in contrast to the other two effluents, is a dry fertilizer, which is quite well known. You can sell it, you can use it for plants. It's it has a, yeah, it's just accessible, and it can of course be sold and has another value. So this is just another value-added product to the whole process. So if you go into detail of the how we do it or how we access the nutrients, you can see that we have this dewatered solid from the TORWASH process. We do a solubilization of the phosphate. This is done via acid leaching. And then afterwards, this is again pressed so that we get a phosphorus-rich extract and a phosphorus-depleted residue. And this extract is mixed with the original liquid effluent, which contains high amounts of ammonium nitrogen. And together, this can form a struvite if we increase the pH up to a certain value by the addition of NaOH. And we've first done this in the lab for the paper sludge, and afterwards also in our mini plant scale. So this is how the mini plant scale looks. On the left, you have the extraction unit, which is a tank where it's simply mixed, a stirred reactor. Then we have this laboratory filter pump. And afterwards, this was the most important part, you could say, it's our airlift reactor. So this is several tubes, one inside another. You have a cone down here where the product, the struvite, is collected. And the whole reactor is agitated by, or the circular movement is induced by air which is bubbling through the reactor. Now, just a brief step back, because this is also interesting. We had several tests with different acids for the leaching and for the extraction of phosphorus. As you can see here, it's the P extraction is on the y-axis, and on the x-axis we have the pH. We could even go lower in pH, but we did not, because first of all, this has several costs, because you need more acid and you need more base afterwards to come back from pH, from the low pH. And secondly, at a certain point, you start to solve a lot of stuff which you do not want, like for example, the heavy metals if you go too low. So that's why we chose this range of pH, which you can see here. And in this range, we had sulfuric acid. Of course, it's relatively cheap and it's a strong acid. We had the organic acids like citric acid combined with the sulfuric acid and the oxalic acid, because the idea was that this might form complexes with specific metal ions, which you saw before, and maybe keep them in solution so we don't get them in our precipitate afterwards. Yeah, we chose these two afterwards, a relatively high pH of 1.8, and from here not a lot did happen anymore in those two cases, so we chose them for further experiments. And then we went on for lab scale trials and for mini plant trial, as I told you before. In the lab scale, both performed quite differently. You can already see this from the color. So as I told you, struvite is white usually, so you have obviously the most pure struvite from the sulfuric acid with citric acid, and the oxalic acid produced a less pure struvite. But if you compare the yields and the P recovery, we got 91% of recovery in this case from the solution, not from the overall biomass. It was 91% from the solution and 78% if you calculate it on the biomass, on the original phosphorus content. And in this case, on the left, we had a P recovery of 45%, or calculated on the biomass, 35%, but a purity of 84%. So this can really be seen as high purity struvite, while the other one probably has to be treated additionally, which means we cannot use it directly as a fertilizer, while we can use this one. Overall, the ammonia recovery was mediocre, 40 to 50%, so not a lot of difference there. And we chose the oxalic acid for further processing, because we thought that the overall phosphate removal was the more important part in the whole procedure. Yeah, and in the mini plant, just very brief, we did receive recoveries from biomass of 38%. So in comparison to the 78 we had before, this is much less. And we found that there is a lot of work to be done, because the extraction unit simply needs to be optimized. The mixing conditions were not optimal. We had a drying out of the filter press cake, so it was just a lot of practical issues which we found there. Okay. Now let's move on quickly to the other two feedstocks. As I told you already, it makes not a lot of sense to try to get phosphorus from the solid because there is no, or almost no phosphorus in. So we tried an approach of a direct struvite precipitation from the filter press effluents in those cases. Again, a similar scheme to before. So we have the normal process. We have olives and oranges, which obviously need fertilizer. We have the usual processing, and then again we have the TORWASH with the filter press effluent and the dewatered solid. And again, first possibility would be maybe we can directly recycle the effluents as liquid fertilizer. Of course, this is again dependent on what is inside. Is it maybe phytotoxic or not? And what are the fertilizer regulations in the country where you want to use it. Second possibility, again, the anaerobic treatment, and afterwards use the digestate as a fertilizer, or in our case, phosphorus precipitation, as I told you, directly from the effluent. And also we did have a look in the digested effluent, or the precipitation from digested effluent, but I'm not presenting this here because of reasons I told you before. And we did this in lab, and the results are quite obvious. We got something, but it's not really pure struvite. So as you can see on the picture already, it's very impure. There's a lot of organics in both of those precipitates. And if you look at the values, we see that we have a phosphorus recovery from the solution of 50 to 60%, but ammonia recovery of only 13 to 15%. So if you remember, it was in struvite, both are present, ammonium and phosphorus. And this already gives you a good hint that there is a lot of phosphate in other forms, which in other phosphorus salts, maybe also organics, but not a lot of struvite. And this was what we also found out there. So if you try to make it in a similar manner as I did before, we had to add ammonium and magnesium in the case of olive pomace to get a favorable ratio for supersaturation so that we can precipitate the struvite afterwards. Then again, we had to use NaOH to make basic again. And if we just look at the results, we had a mediocre P recovery in both cases of 50 and 60%. So 50% for the olive pomace and 60% for the orange peels, but the precipitate purity was quite bad and even worse in the two cases. Okay, now what can we conclude from that? Obviously, the feedstocks provide specific nutrient contents, mobilities, and availabilities, and different approaches for recovery are needed. That's what we did, and that's what we think will really be needed for each specific case. So there is, from our view, no one-fits-all solution. If you look at the paper sludge, we had the highest nutrient content, so we think this is most suitable from the three biomasses we had for our kind of struvite recovery. It has the highest heavy metal content, but this should not be a problem because usually it does not go into solution from our leaching. And then we can reach a P recovery of 78% lab scale, and in this case 38% in the mini plant, but I already told you there were several problems in the extraction unit and not so much or almost not in the precipitation unit. So this just is engineering and it's just iterations of just making it better, and then this will work. For paper sludge, also we have limited knowledge for direct integration of the nutrients to the or the nutrient recovery to the wastewater treatment process. This just has to be researched. And we think the production of struvite-based mineral fertilizer is or can be feasible for this biomass. Lessons learned for the acid leaching is, of course, we need to reduce the acid consumption. We have to avoid impurities if we can. So we think about maybe chemical complexation as possible, as I explained it before. We have to improve the resuspension of the press cake, and maybe also an idea would be to integrate this with a filtration step. This again has its own problems because of the buffer capacity of the liquid, and so maybe you need more acid, but we have to look into that. For olive pomace and orange peels, most of the interesting nutrients, or phosphorus at least, and potassium were in the liquid phase, so there was a good separation, and immediate struvite precipitation is an option. However, as you saw, struvite yields and purity are low, and this, of course, has an impact on marketability and economic performance. And as we think, as we also saw before, the high organic content of the effluents is rather interesting for the anaerobic co-digestion, and maybe, or in this case, the direct use of the digestate as organic fertilizer, because you also saw that precipitation did not work that well from the effluents, and I didn't show this, but it also did not work well from the digested effluents. Yeah, so to give you an outlook, for paper sludge, we would need to further develop the process. We would need to upscale it. Then as a next step, we need fertilizing tests in lab and in field. And of course, especially for the direct integration in the wastewater treatment process, you need assessments of feasibility, cost effectiveness, and additional benefits. And for olive pollens and orange peels, we think best way would be to directly use the co-digested effluent as an organic fertilizer. And here you also have to check the fertilizer regulations, depending on where you want to use it. And of course, you could start with an analysis of a hydrocarbon species to estimate ecotoxicology towards soil bacteria and plants. And afterwards, it's again fertilizing tests with real plants and organisms. So I hope, I mentioned everything you're interested in. I thank you a lot for the attention, and I'm open for questions now, of course.
Yes, any questions from the floor?
Hi, thank you for your presentation. I was interested in this paper sludge case because you say it might be interesting to recover the struvite there. I have two questions about that, because in the paper process itself, I think they are adding nitrogen and phosphorus to the wastewater treatment plant to keep it going. So from that point of view, would you think it's more beneficial to recover the struvite or to return the filtrate or the digested filtrate back to that treatment plant?
That depends. It depends first on how good this works. We think if without a lot of treatment and without a lot of disruption in the process, you can directly recover it, it would make most sense. Because struvite, I mean, right now the prices are rising a bit, but we're still at about $300 per ton roughly, so this is not a very high grade or high value product. And so if we get this direct recovery or this direct recycle, I think it would be most beneficial. However, I'm not sure if this works in practice. We would have to test that.
Yeah, well, I agree with that. Then a second question about, let's assume you do recover struvite there. To recover the struvite, you have to add extra magnesium. And after recovering the struvite, you have, let's say, still the filtrate, but then with extra magnesium. And if you then close the whole cycle, you will probably end up with more magnesium in your solid product. Or do you think it would still distribute mostly towards the liquid phase?
I think it completely depends on how we adjust the amount of magnesium. I mean, in the first place, we do this. What we also thought about or tested at several points was that you could directly acidify the whole slurry and try to use this as a precipitation directly. That you don't need an initial separation of the liquid and solid phase, but directly do it in the slurry. And one of the reasons we are not doing this is because if we separate it before, or we do the separation before, we have a better understanding of what is inside, and we can adjust the different proportions better. So I think this is not that much of a problem, because you know the stoichiometric ratio, you know how much you need, and you know approximately how it will precipitate. So I don't think there will be so much left. But I can forward this question to Gero if you want.
Okay, thank you. I can discuss with him later. Yeah. Thank you.
Hello, Manuel. This is Levine from TORWASH. Thank you for your very interesting results. I have one question about the presence of the phosphorus at the source material. Some of the wastewater treatment plants also add like chemical bonding binding of phosphate, and others apply like a biological binding of the phosphates, and that the stability they adding for the chemical way they're adding like iron or aluminum salts, and then iron phosphate and aluminum phosphates are but these are really stable. So did you find out what type this paper sludge, what type of phosphate binding was used? Because it really determines your leaching process, of course.
Yeah. Sorry, I have no idea about that.
Okay.
I'll forward it together.
Maybe I can comment on it, because I think they're only adding the phosphate purely for biological growth. So I don't think it's chemically bound. It's really in the biomass that's then falling apart.
Hi, thanks for your presentation. I have a question regarding the phosphor content in the solid sludge product, because we cared a lot about the phosphor content in the product in steel making process, because phosphor is kind of hazardous material, or I would say harmful element in steel making. To remove the phosphor from steel, we need to add a lot of calcium oxide into the slag to remove the phosphor, which means we will have a lot of byproduct produced during the smelting process. Yeah, in your slides you listed some data regarding the recovery rate of phosphor, and you mentioned for the lab scale test the recovery rate is around 75%, and for the mini plant test is around 38%. Yeah, of course we can calculate the phyto content based on the recovery rate, but do you have any exact data for the phosphor content in the phyto product?
I'm quite sure we do have. I don't have it here, but I mean this was based on the biomass. So usually you should use the number from the sludge. So because there it was higher, it was 91%, which we were able to remove from the solid. If this was your question, I can have a look for the precise data. I don't have it here, but 91% was what we were able to remove from the solid, and just the calculation back on the original biomass was the 78.
Okay.
Because some was also in the liquid. Was that understandable? I will have a look at the data, but yeah.
Yes, understandable.
Yeah, that's great. Thank you.
It can be calculated based on the recovery rate, but yeah, I just want to know some exact data. But yeah, that's fine.
Okay.
Thank you, Manuel.